All right, so the seating chart is up. You can go ahead and do the seating chart. And then you're going to need iClicker. You need a calculator. You need your best friend. All kind of stuff. All right, y'all ready? Okay, I think yesterday, last time I saw y'all, I think I forgot to tell y'all a joke. Did I forget to tell y'all a joke last time? I think I did. So, okay, so I owe you two. What does a dog say when he sits on sandpaper? Wow, that's rough. Let's see. Which reindeer called Rudolph names? Olive, the other reindeer. Not all of the other, but Olive, the other reindeer. Olive. I didn't say they would be good. Okay, so you can go ahead and get your iClicker out. Which one are we on? Let's see. Let's see. I think it's gonna be this one. Nope. This one. Okay. All right. Make it all on one screen. Okay, so here you're going to select the correct equation for the neutralization reaction of H2SO4 and KOH. I'm going to suggest you get out a sheet of paper. I notice I haven't started the clock yet. Get out a sheet of paper and write the neutralization of H2SO4 and KOH, and then compare your answer choices to what's here. Okay, so I'll give you a full like 2.5 minutes to do it. But it always works better if you write it yourself. So 2.5 minutes. 2 minutes, 30 seconds. Remember, 2 minutes and 30 seconds. Okay, 15 seconds. Make sure you try. Okay, make sure you've clicked in. All right, so turn and talk to the people around you. Compare answers. Make sure you click in for a second time. Don't forget to do that. "45 seconds for that second click in. Okay, make sure you click in again. We had more than 42. Click in again. Okay, so what did we say? Oh, very nice. Good job. E is the correct answer. So we definitely saw a huge improvement. What did you have to worry about when you were doing this? You had to balance, but you had to balance the equation. But before you could balance the equation, what did you have to worry about? The charges, right? So we know we're taking oxygen and hydrogen, right? And we're going to make what? We're going to make water. And then we're going to have SO4, which is a polyatomic ion, right? And we're going to combine that with potassium. So SO4, what's the charge on SO4? SO4 -2, what's the charge on K? +1. So when I take these and I do the crossover, I get a 1 here and I get a 2 here. So I rewrite my formula as K2SO4, right? So once you did that and plugged that in, now you have to worry about balancing. But you should have recognized that you had 2 hydrogens here, right? So what you end up having to do is to have 2 OHs here to make 2 waters. And then when you put that 2, you also balanced the potassium. Yeah? You'll see something like that on your next exam. Okay. What are the products of the reaction of hydrochloric acid and NaHCO3? What do you get? You should recognize this type of an equation. 10 seconds. This one you don't have to balance, you just have to know what the products are. Okay, so now you can turn and you can talk to the people around you. Mask up, everybody, mask up. Okay, 5 seconds. Make sure you click in again. All right, so what did we say? Good, very good. Very good. So how did you realize that? We need water, carbon dioxide, and salt, right? Where did the salt come from? Na and Cl, right? Where did the water come from? The hydrogen, that's right, we want H2 and then O. Where's the oxygen come from? It's one of the oxygens here. So then what's remaining is CO2, right? So we made water, we made carbon dioxide, and we made NaCl. So what kind of a reaction is this? Neutralization. Okay. All right, last one. We did this in class. This was lots of class, right? how does the addition of ammonium affect the equilibrium of the reactions shown here? So here's ammonium, and I put it right there. So you tell me what happens to this reaction. Write it down. We do this, the reaction does that, this is the shift. Write it down. Okay, 5 seconds, make sure you click in. Okay, turn and talk to the people around you. 45 seconds. Ten seconds. Okay. So when you were doing this, basically, which two, if you change something, it has to be either a left shift or a right shift, right? So should you have even looked at C and D? No. So really you had a 50-50 shot on this one, right? So what did we do to the reaction? The addition of ammonium, we increased a reactant or a product? Reactant. So what did the reaction do? Decrease reactant. How do we get rid of reactants? We shift this way. Is that left or right? That is right. So what do we say? Ooh, we're pretty divided, but we narrowed it down. Y'all do so well when you talk to each other. I really like that. I think that's been working pretty well. Have y'all been enjoying that? Think that's helpful? All right. Okay, so let's go do some chapter 9 stuff. We were on, how far did we get? 9.34. 9.34. Okay. And don't forget to start working on the exam material and doing that extra quiz. Okay. So the two things I talked about yesterday, Tuesday, you full screen. Okay. So we did A, didn't we do A? Right. So we're identifying the acid base on the reactant side, and then identify the conjugate acid and conjugate base on the product side. So let's take our first reactant and track it over and see what happens. So did it accept a hydrogen or did it donate a hydrogen? It accepted a hydrogen. So what do we call substances that accept hydrogens? We call them bases. So this is our base. And what is HCO3 minus? Conjugate acid. Good. Okay. So then what is H2O in this case? This is our acid. And what is OH minus? Conjugate base. So what is the difference between the acid and the conjugate base? What happened? We lost what? A hydrogen or a proton. We lost that hydrogen. So do you see how the formula is one less hydrogen? But now there's something else about the formula. What do you notice about the formula? When we went from H2O, H2O is neutral. Is OH neutral? No, it's charged, right? Because that hydrogen ion carries a positive charge. So look at CO3 2 minus. When it goes from being a base to being the conjugate acid, what happens to it? It is going to lose, it's not going to lose, it is going to gain a hydrogen, and what else? Went from a went from a -2 to a, why do you go from a -2 to a -1? What happened here? We gained a proton. We gained an H plus. So we got one more positive charge. So we are, instead of being -2, we are -1. So watch that when you're doing these. Okay. C, H3PO4, excuse me, going to H2PO4 minus. What happens? Donate or accept hydrogen? Donate. Okay, so we call H3PO4A. An acid, right? If you donate hydrogen ions, you're an acid. And then H2PO4 minus is the okay. So what does that make in H3? Remember we said NH3 is a base. It's a weak base, but it's still a base. So then NH4 plus is the conjugate acid. And look and evaluate, when we go from base to conjugate acid, do we in fact gain a hydrogen atom and a positive charge? Yes. When we go from H3PO4 to H2PO4 minus, we lose a hydrogen and we lose a positive charge. Okay. All right. So that's really important for this, right? Because now we have to write the formula and the name of the conjugate base that's formed from each of the following acids. So what I'm saying is A through D, all of these are acids. So what are they going to, how are they going to behave? Donate or accept hydrogen ions? Donate, H plus. Okay, so let's look at A. If I'm going to donate an H plus, what do I become? CO3 is the correct atoms. Now, what is my charge? I'm going to donate a positive charge. Means I'm going to get rid of a positive charge. So 2 minus. Now we have to name it. How do you name this? Do you have to remember? No, where do you go? This is a polyatomic ion. It's many atoms that are charged. Where do you go? Go to your best friend. What is CO3 2 minus? Carbonate. Carbonate. Okay, B. B is going to be an acid. So we're going to donate a hydrogen ion. We're going to get rid of a hydrogen ion. What do we become? Just H2O. So you could call this water. How else could you call it? Dihydrogen monoxide. Okay. HPO4 2 minus. We're going to lose a hydrogen because it's an acid, and we're going to end up with PO4. What's my charge? 3 minus. Go to your polyatomic ion table. What do you find? That's right, phosphate. Last one, HNO2. We lose the hydrogen, so we're left with just NO2, but what should my charge be? Negative. And that makes me what? Nitrate or nitrite? Okay. No, nitrite. Nitrite. Okay. Now we're going to do the same thing, except we're going to write the name and the formula of the conjugate acid that's formed from a base. So now we have to go in the opposite direction. So if everything here is a base, what is it going to do? It's going to accept what? A hydrogen ion, okay? So how does SO4 2- accept a hydrogen ion? Just put a hydrogen on the front of it, and you end up with SO4, and now all you have to do is worry about the charge. So if we're -2 and we pick up a hydrogen, what is my charge? Minus. So now I'm going to go name it. Now, a lot of times you have, if you're talking about making a conjugate acid, it's not a true acid. So this is charged. So technically it's a what? Technically it's a polyatomic ion. So you could name it either as an acid or you could name it as a polyatomic ion. The easiest thing to do is just name it as a polyatomic ion, because that's where it is on your table. So go look it up. What is HSO4-? Hydrogen sulfate, right? There was another name, bisulfate, right? So the reason that a lot of times we do this, we say this is the hydrogen sulfate ion. So we know that it's a polyatomic ion. If I were to pick up one more hydrogen, I would end up being H2SO4 and I would have no charge. Now, what do we call this? Is it charged? No. And this is an acid. So what do we call it? Sulf. And remember aticitis. ATEICITEOUS, right? So SO4 is what? Sulfate. So ATE becomes IC, sulfur, UR, I missed the UR, sulfuric acid, right? So that's only if you pick up another hydrogen, but it's cool. Just name it by what you have. Okay. CN-. What do I do to make that a conjugate acid? Add a hydrogen. What's my charge? No charge, right? Because I picked up one positive. I had a negative and I picked up a positive. A positive plus a negative is 0, right? So now how do I name it? Go to your polyatomic ion table. What is CN- called? It's called what? So it's called, this one is cyanide. So if you end in IDE, what's the rule? Now I know this one's kind of weird because usually things that end in IDE are where? On the periodic table, right? So if I said HCl, right? What do you call HCl? Hydrochloric acid, right? So you did hydro, you added the IC and you put acid. Cyanide is an exception to the binary acid rule, right? Remember we said if there were two atoms, this is what you do. But cyanide is one of those things that we write this way too, even though it's on the polyatomic ion table. So how would I name this in this fashion? I would have hydro, RO, hydro, what? Cyanic acid, because I put ACID. Oh. Right? Because I got the hydro, I got the IC, I got the acid. Yeah. Okay. ClO minus, ClO2 minus. This is, they told you, the chlorite ion. So ITE becomes what? ITE becomes what? OUS. So what do we name this? Chlorous acid. And what's my formula? HClO2, uncharged. Okay. So acids can be neutral and acids can be charged. It kind of depends on what's going on. Question? I skipped C. Oh, I did. Thank you. Okay, so C, we're going to pick up C. C is going to be over here. Ooh, not A, C. Okay, so what do? Just put a hydrogen on it. What do you get? H2O. What do you call it? Water or what? Dihydrogen monoxide. So can acid function as an acid? Can water function as an acid? Yes. Can water function as a base? Yes. Yes. All right. Okay. So now we're going to kind of combine everything that we've done so far into some chemical equations. So complete the reaction and identify conjugate acid and base pairs if the named reactant acts as a base. What does a base do? Accept or donate hydrogens? Okay, so I always like to write that. That's one of those things, like if I were taking the exam, I would actually write that on my exam. That way, you don't have to just think about it, it's there. So let's predict our products. So it's telling me A, that this whole thing right here is pyruvate. Pyruvate is a product of glucose metabolism. So when it goes through glycolysis, you're going to make pyruvate. So we have to predict what's going to happen. We're told it's an acid-base reaction. So if pyruvate is acting as a base, what is it going to do? It's going to accept a hydrogen. How do you know where to put it? Usually, go and find the charge. Do you see one of the oxygens has a negative charge? Do you see that? So this oxygen has a negative charge, whereas like this oxygen does not. So you're going to put the hydrogen on the oxygen that has a negative charge. So you rewrite the whole molecule, CH3, CO, C, come on, OO, and then instead of writing the minus, put the hydrogen. So if this is the base, what did I just draw? The conjugate acid. I'm just going to abbreviate it, Ca, conjugate acid. Okay, so if pyruvate acted as the base, what is water acting as? The acid. So then how do I draw? If I have an acid, I want to make a conjugate base. How do I draw that conjugate base? I would draw it as OH minus, right? Why is that? Hydrogen has donated a hydrogen ion. Questions? Pretty good? Okay, let's try another one. I'm gonna erase down here just so I have room to write my reaction. Okay, so H2PO4 minus, which is dihydrogen phosphate, a component in cell buffering. We're told in the problem that this is a what? This is a base. So water must be acting as an acid. Okay, so now I want to take my base and turn it into the what? Conjugate acid. So how would I draw that? When I go from being a base to a conjugate acid, I'm going to accept a hydrogen. What do I become? We had H2, so we need to accept a hydrogen. So H3PO4. And then we're also going to make something from water. Water's being an acid, we're going to turn it into a conjugate base. So what happens? It just loses the hydrogen and becomes OH minus. Okay, the last one, HCO3 minus is acting as what? It's acting as a base. So the water is acting as what? An acid. I'll change colors. So if I take my base and I want to turn it into a conjugate acid, a CID, what do? A base is going to accept a hydrogen ion, so I need to go H2CO3. Do I have a charge? No charge. That was free advice, right? And then what happens to my acid? Turn into a conjugate, JUGAT, conjugate base. And the conjugate base, I heard Del saying, is OH minus. Not too bad, right? Okay, I want to point out something. If you were watching the video and you completed these up above, do you see this bicarbonate is HCO3 minus? And what is it saying in this question that this is acting as, an acid or a base? An acid. Come down to C down here, bicarbonate. What is it acting as? A base. So there are substances that can act as both. So act as both an acid and a base. Wow, that's kind of cool, right? We call those molecules amphoteric. Amphoteric. So if you do the same thing, if you look at B was dihydrogen phosphate. It's the same thing. It acts as a base in this question, and in the previous question, it acts as an acid. So you're going to see that it can go both ways. Okay, pH. pH is so super important. So when we talk about pH, we say either basically you have a high pH, a low pH, or you're neutral, right? So if you have a high pH, are you basic or acidic? You're basic. So this is a quote unquote high pH. If you have a low pH, that means you are acidic, right? Okay. Neutral means you're at pH 7. Means you're not high, you're not low. You're just neutral. Are we neutral? You and I, in our bodies, physiologically, we are not neutral. We are not. We have what's called physiological pH. It's not neutral. It's about 7.35 to 7.45. So technically, we're what? Technically, we're basic. Technically, we're a little bit basic. Okay? So when we talk about pH, what is pH? What does the P stand for? It stands for negative log. So if you're looking at your calculator, and I'm going to switch screens here, see if I can do this. Put up one of them. You have one of these two calculators, right? If I can zoom out a little bit. You have one of these two, correct? Most people have the smaller one. Yeah. Okay, so I'm going to pick one and I'm going to show it, and I'll try to go back and forth. But what does P stand for? P stands for the negative log. So if you're going to do this in your calculator, do you see that you have two negative signs? You have one that is a minus, and you have one that is really a negative. The one at the bottom, if I do negative log, I have to press this one. So I press this one negative, and you see how the negative sign, the negative sign is smaller. So negative log, here's log. This, it's the button right under second, press log. And that's what you get, right? So that's what we're going to be doing. Anytime you see P, that's what you're going to put in your calculator, negative log. Okay, so to get the pH of something, we're going to do the negative log, the concentration of H plus or H3O plus, right? Because we said that's the same thing. H3O plus is really the same thing as concentration of H plus, right? So pH is a measure of how many hydrogen ions you have floating around. Okay, so let's look at some solutions and let's identify them as acidic, basic, or neutral. If I have soda that's pH 3.2, acidic, basic, or neutral? Acidic. Shampoo. This one's acidic. Laundry detergent. Basic because I'm above 7. Rain, pH 5.8. Acidic. Acid rain has a very low pH, right? Okay, state of each of the following solutions is acidic, basic, or neutral. You could go and you could learn, if I scroll up, the H plus concentration, because that 7 actually ends up being the exponent over here. It becomes a negative exponent. But gosh, that's kind of a lot to remember, right? So why not just take it and turn it into pH? How about we do that? And then it's very easy, right? Because are you going to get this pH, acidic, basic, and all that on your equation sheet? Please tell me, are you going to get it? Yes, you have this on your best friend. So if I want to do pH is equal to the negative log concentration of H plus. What's my concentration of H plus here, or H3O plus? 5.6 times 10 to the minus 10. So I'm going to show you, I'm going to switch back over to my calculator over here. Okay, so I've got negative log. I'm going to do, let me zoom out a little bit so you can see the whole calculator. Okay, so I'm going to do 5.6. Now I need to do times 10 to the negative 10. How do you put that into a calculator? You do second, and then do you see x to the negative 1 has a teeny tiny EE above it? Press that. So that E represents the same thing as times 10 to the, and then put negative, not minus, but negative. What do we have? 10. Close parentheses. hit enter. What do you get? There are multiple ways to do it. If you do it a different way on your calculator, there are multiple ways to do it. As long as you're getting the right answer. I want you to plug this into your calculator right now. Everybody do it. The calculator that you're going to have on your exam. So what do you get? 9.25. Okay, so now can you tell me if that's acidic or basic? That's basic, right? That's really easy now. Do the same thing for B. pH is equal to the negative log 6.2 times 10 to the minus 8. So let's do that. So we're doing negative log 6.2 second EE to the negative 8, close parentheses. 7.21. Am I basic? Am I neutral? Am I acidic? I am basic. I'm not neutral, y'all sure? Yep, unless I am exactly 7, I'm not neutral. All right, C, what do you get if you plug it into your calculator? What do you get? 1.3. I'm going to switch back to my computer because now that y'all know how to do that, right? Okay, so if you're 1.3, are you acidic or basic? Acidic. Okay, how about D? What's my pH? 5.74. And in pHs, your number of sig figs in concentration of H3O plus is equal to the number of places past the decimal in pH. You don't have to really memorize that. It's going to be multiple choice. So you're not going to be really worried about sig figs, but I want you to realize that it's different. So D is acid or base or neutral? Acid. Okay. All right, calculate the pH of each of the solutions in 4.4. So we just did that, right? In 4.4? 4.3, yeah, 4.4. So we already did that. Check, done. Okay. Oh, did I not do this one in the video? I did the wrong one? Haha. All right, calculate the H3O concentration for each of the following measurements of pH. Drain cleaner. pH 12.01. Oh, this is different, right? My formula was pH is equal to the negative log concentration of H3O plus. And in the past, I've been asked to solve for pH, right? But what's given? pH. So I have to calculate concentration of H3O plus. So how do I do that? So let's isolate it mathematically, right? If I have a negative here, I can divide by -1, right? By -1, and I would get negative pH is equal to the log concentration of H3O plus. What's the opposite of log? Look on your calculator, find log, and look what's above log. What's above log? 10 to the x, right? Y'all see that? So if I take both sides of the equation and I do 10 raised to the negative pH and 10 raised to the log of H3O plus, basically what that does is eliminates both of those things. So if I do 10 raised to the negative pH, I get the concentration of H3O plus. So I'm going to show you how to do that on the calculator. Okay. As I was pressing buttons, right? Okay, so let's do A. Let's do A. A is 12.10. So I take 10 raised to the negative 12.10. And what do I get? So I'm going to do second log, right? And I'm going to type in negative, not the minus, but negative 12.08. So, oh, I did it wrong. It's not supposed to be 12.08, 12.10. Sorry, y'all. So second log, negative 12.10. What do you get? 7.94. 7.9. Is that right? 94 times 10 to the what? Negative 13. Everybody get that on their calculators? Yeah. So one of the other things, you have to kind of look at your calculator settings, right? So sometimes you'll be in scientific, sometimes you're in flow. And if you have a smaller exponent, it's going to show you things a little differently if you're in flow versus scientific. So if you're not seeing it in scientific notation, go second, and it's DRG, and pick scientific. Right? And it'll show it to you in that way. Good. If you have an issue, come and let me help you at the end of class before you walk out the door. If you're not getting these numbers, make sure you come up and get some help before you walk out the door. Okay, coffee pH 5.5. So B, you just do 10 raised to the negative 5.5. What do you get? What should you get? So it's one place past the decimal. So really this one should have been just like that. So it's really one place past the decimal. So really it's just 3 times 10 to the negative 6. So what are my units on this? I didn't have a unit. What is my unit? What is concentration? No, because it is one place past the decimal here. I'm sorry, what? It's 3.162. Yeah, but we're looking here, right? So our pH is given in one place past the decimal. So we only have one significant figure in our answer. So I had gotten that too, and I had to put it in scientific. And put it in scientific. So try to put your calculator into scientific and see what you get. Because I was getting the zeros. The zeros? But the number of sig figs that we're using is the number that's behind the decimal. So correct. The first one, there was 2 numbers behind the decimal, so there was 2 sig figs. For the second one, there's only 1. Correct. And the decimal on the sheet, like not what's on the calculator. Correct. Correct. But you won't have to write them, right? You'll pick an option. So it doesn't really matter how many significant figures, right? Because you'll just pick an option. And I promise the options won't differ just by significant figures. I'm not going to do that to you. Okay. So don't worry about that. All right. So C, let's do C over here. C, gastric juice, pH 2.00. So see how we have 2 places past the decimal? We're going to give it 2 significant figures. So we do 10 raised to the negative 2. What do you get? You get 1.0 times 10 to the minus 2. Oh, and I was talking about units and we never answered that. What kind of units do I have? What is concentration? What's the unit of concentration? Big M, which is really moles per liter. So these should all be big M. Okay. How about D? 10 raised to the negative 8.3. What do you get? And we're only going one significant figure, so 5 times 10 to the negative 9. Yes, ma'am.
One at smaller C It doesn't give me the charge 10 to a large part. Or that's what I'm looking for.
All you have to do is convert from regular to scientific notation.
Oh, yes.
All you have to do is convert to scientific notation. So if you get something that is 0.0001, you could have an answer choice on the exam that writes it in scientific notation. So how do you write it in scientific notation? 1, 2, 3, 4, 5. So this would be 1 times 10 to the -5. So yes, you have to be able to do that. But the trick is on your calculator, if you do second and then the button immediately to the right says DRG, you press that and you select scientific and it puts it in scientific notation for you. Okay, good. Okay. All right, so next thing we're going to talk about is we're getting more physiological. We're talking more and more, not just about acids and bases in general, but kind of how they work inside the body. So when we talk about acids and bases, remember earlier in the chapter, we talked about the K. What is big K? It's the equilibrium constant of a given reaction, right? So you can pick any of your acids, right? And you can find the Ka of that acid, right? The Ka of any given acid is products over reactants. Remember this? And the stronger the acid is, the more what you make. You make more products or you make more reactants? If I go HX goes to H plus plus X minus. Do you have more reactants or more products? You make more products, right? So you make more products. So tell me about the Ka value for things that are stronger acids. Are they bigger or smaller? They're bigger. So if we look, here's a strong acid and it's only 1.2 times 10 to the -2. I come down here and I find my weakest acid possible, which is water. Look at that Ka value. Holy moly. That is 1 times 10 to the negative what? 14. That's really tiny. Okay, you can do that. But a lot of times people have a hard time looking at something that is times 10 to the something, right? This is why the pH scale was invented, so that we wouldn't have to look at concentration values. So we can have a Ka, but we can also have a pKa. So a pKa is equal to the negative log of the Ka, right? Because P just means negative log. So if I have something that's 1 times 10 to the -2, that gives me a pKa value of 2. If I have something that is 1 times 10 to the -14, it gives me a pKa value of 14. So the numbers, it makes the numbers a little easier. So if you want to talk about pKa values and strengths of acids that have pKa values close to 1 are stronger. So do you see how the strongest one has a pKa value of 2? 2 is really close to 1. What does water have? A pKa value of 14. That's much farther away from 1, right? I told you this chart was going to be important, right? Okay, so now we need to be able to look and say which one of these is going to be stronger just by knowing the pKa value. So HCl or HCN. What do you know about HCl? It's not even on there. Why is it not on there? because it's a strong acid. So do you even need numbers to compare? No, the stronger acid is the strong acid, hydrochloric acid. Acetic acid and ammonium ion. What's the pKa value for acetic acid? Go up and find acetic acid, 4.76. What is it for the ammonium ion? So which one is the stronger? Acetic acid. It is closer to a value of 1. Carbonic acid. What's my pKa value? How about bicarbonate ion? Which one is the stronger acid? Carbonic acid. All you're doing is finding the one that's closest to 1. Ammonium ion. What do I get for a pKa value? 9.20. What do we get for hydrogen phosphate ion? Oh, I didn't mean to circle it. Just meant to put an arrow. What do we get? So which one is stronger? The ammonium ion. Pretty simple, right? Yeah. Okay, so now you can look at different drugs, and each drug has a unique pKa value, and that pKa value controls how this drug behaves in a patient's body. And we're going to talk about that next. So what's the stronger acid, niacin or acetyl salicylic acid? Y'all know what acetyl salicylic acid is? Aspirin. So which one of these is stronger? Acetyl salicylic acid. Okay, all you're looking at is that pKa value. Okay, so now we can talk about acids and bases and drugs and how it works in the body. So before we talk about this, I want to say a few words, and I'm going to come down here because I want to mess up what we're doing. So medications that we take, right? Drugs that we take. A lot of times we want drugs to have particular characteristics, right? I want a drug that's going to be soluble, right? So we want it to be soluble. What do we want? Soluble. S-O-L, no. U-B-L-E, soluble. So why do we want a drug to be soluble? What can we do if we have a drug that's soluble? We can take it as an oral medication. We could also put it into a syringe if it's soluble. If it's not soluble, you can't put it in a syringe and inject somebody with it. That's going to be not good. We want it to be soluble. Soluble in what? In water. Water is what? Acid or base. It can act as either. It's polar. If we talk about solubility, like dissolves like. So we want something that will dissolve in water. If something is polar, it'll dissolve pretty well. What about something charged? Oh, awesome, right? So because we want them soluble in water, we want them charged, because then we'll have what kind of an interaction? An ion dipole interaction, and that's going to be phenomenal. It will be super soluble. That's awesome, right? Now, here's a problem. We also want it to cross the cell membrane. Do we want it to be charged? What do we know about cell membranes? Are they letting charged things by? Absolutely not. So what do we need to get into the cell? Something that is neutral. Did you see when we were writing those acids and the conjugate bases? Sometimes you had something that was charged and then it lost a hydrogen and it became neutral, or it gained a hydrogen and then it became neutral. That's how drugs work. Have you seen a lot of the sinus congestion medicine? It'll say something HCl. Have you seen that before? It's because it's functioning as an acid or functioning as a base. So let's talk about how that works, right? So if we come up here, okay. So here's an example medication. So this is valproic acid. It's an anticonvulsant. It's represented as its acid form in this picture. Is this charged? Do you see a positive or a negative? No. So this is neutral. If it's an acid, it can undergo a reaction and it can form a conjugate base, right? What happens when we go from an acid to a conjugate base? Gain or lose a hydrogen. We're going to lose a hydrogen. Do you see a hydrogen in this structure? There are many, but we don't draw them, but there's one that we see. That is the hydrogen that we're going to lose. So all I have to do to draw the conjugate is to draw exactly the same thing. But now what? Don't draw the hydrogen, but what happens? Put a negative. So the conjugate base form is charged. So the conjugate base form is what I want to solubilize it in. Then I want it to convert to the acid form when I inject it into somebody or when I orally take it, right? So let's read our questions. Which form is charged? Acid, or conjugate base, or both? Just the conjugate base. Which form will predominate in the first part of the small intestine, the jejunum, where the pH is between 6 and 7? How do we figure that out? Well, you go up. This table tells you the relationship. And if you look, does it do this one? I didn't do this one. So this is what you have to know, right? If my pH is less than my pKa, I'm going to have more acid present, right? Because what is that telling me? It's telling me that I'm going to keep the hydrogen attached, right? So I'm going to keep the hydrogen, whatever, if that's charged or uncharged, doesn't matter. It's keeping the hydrogen. If I have a pH that is greater than the pKa, that means that I've formed the conjugate base. So what's happened? I've lost the hydrogen. In the acid form, I'm going to keep my hydrogen. But what happens when my pH is equal to my pKa? I'm going to have half that keep the hydrogen, and I'm going to have half that lost the hydrogen. So I'll have an equal amount of acid and conjugate base. Okay, so we're always comparing pH and pKa. So what I like to do is I like to say, okay, what is the pH and what is the pKa? So in this question, B, what's my pH? Somewhere between 6 and 7, right? What is the pKa for this substance? So it's told here and it's told here. It is 4.8. Now, which one's bigger? pH. So if you go up here, when pH is greater than pKa, when pH is greater than pKa, what do we have more of? Conjugate base. Okay. So we have more of the conjugate base. Which form, acid or conjugate base, will be able to more easily diffuse through a cell membrane? More easily diffuse, is that charged or neutral? So which form? Our neutral form, which is the acid. So a lot of times you don't want it to go into the membrane when it's in the stomach. You want it to go cross membranes when it gets into the bloodstream, right? So a lot of times, because of those pH changes, you're going to have a difference in how that drug can cross a membrane or not. Okay, so now we're going to talk about a neurotransmitter. I love neurotransmitters, they're so cool. So this one's dopamine. Dopamine has a pKa value of 8.9. So what form is this dopamine in? This is in the acid form. So is the acid form charged or uncharged? Look at this nitrogen. It's charged, right? So the conjugate base form would be neutral, Okay, I'm not going to ask you questions like that on the exam. I'm not going to say what happens on C. So let's look at A and B. Will the conjugate acid or the conjugate base predominate at the following pH values? So if you're at pH 7.5, pH 7.45, excuse me, and we're going to compare it to the pKa, 8.90. What's going to happen? Which one's bigger, pH or pKa? Our pKa is now greater than our pH, right? So what form is going to predominate when our pH is smaller than our pKa? The acid form. Good. Now we're going to change that pH. We're going to go to pH 8.90. We're going to compare it again to our pKa. The pKa doesn't change. Uh-oh. They're exactly the same. So what do we have more of? Neither, they're equal. You have equal amounts of the acid form and the conjugate base form. Okay, so now we're going to go to 13.40. Wow, that's basic. Okay, so now my pH is greater than my pKa. So what form am I in? What do I have more of? The conjugate base. So now at each pH, is that form charged or uncharged? So look at pH 7.45. Is my dopamine charged or uncharged? It's charged. Okay. At 8.9. We have half that's charged and half uncharged. So it's half and half. Right? How about my conjugate base? Uncharged. And then you don't have to be able to do this one. Okay. All right, anesthetics are a really cool drug. In all anesthetics, so all, make yourself a note, all anesthetics, all anesthetics, they are going to be charged in their acid form. And the reason that they're charged in the acid form, in their acid form, is that they have a nitrogen that has 4 bonds around it. And that 4th bond, make sure it has a positive charge. That 4th bond will have a hydrogen attached to it, right? So that's why they're in the acid form. And then when they go to conjugate base, what happens? They're going to lose this hydrogen right here. So then you'll have a nitrogen and it'll only have 3 things attached to it. Will it be charged? No, it'll be uncharged. That's kind of like the background that you need to know about anesthetics. So this is these two drugs that they're talking about here are used in epidural blocks, and they have different pKa's. So we have one that has a pKa of 7.6, and we have another one and a pKa of 8.1. So the question is, when we're designing these drugs, what's a better pKa, right? Well, I want this medication to have as much as I can in the uncharged form at physiological pH. Remind me, what is physiological pH? 7 point, go look. 7.35 to 7.45, right? It's a pretty tight window. So which one is going to be the better drug? Which one is going to be neutral at that physiological pH? And therefore, if it's neutral, it's crossing the membrane and it is going to do its job and numb the patient, right? So how do we decide that? All we have to do is look at the pKa values of the different drugs. So tell me, which one is going to have more of the uncharged form, the conjugate base form, available at physiological pH? Which one has a pKa value closest to physiological pH? Yep, so it's the, and I can't pronounce all of them, but they're all the canes. They all end in cane, C-I-N-E, right? So this one has a pKa value that is much closer to physiological pH. And therefore it's going to act quicker and it's going to block pain for the patient. And that's exactly what you want. You want it to be super fast acting. Isn't that kind of cool? Like, but you have to understand acids and bases to understand how drugs work and why they work, why they cross the barrier, why they don't. Why do they work, you know, when they get in the bloodstream and not in the stomach? All that kind of stuff. So understanding acids and bases is huge. Okay, so anytime that we need to keep a part of our body at a particular pH, we use something called a buffer. A buffer, by definition, has a weak acid and a conjugate base, or a weak base and a conjugate acid. Because their job is to resist big changes in pH. So if I have a weak acid, I can convert a strong base into a weak base, right? So I can make it less damaging for the body. So the bicarbonate system is inside of our bodies, and it controls the pH inside of our blood. Because we have a lot of things that can alter our blood pH, and it can be very, very, very dangerous. So let's talk about this reaction. And now I'm going to preface this by saying this is not a complete reaction. Your book gives you this as the question, but if you look in your book, right, you have water inside of your bloodstream. Most of your blood is water, right? So you have water. You also have carbon dioxide gas, right? This is what you exhale from cellular respiration all the time, right? Carbon dioxide. And eventually you exhale it, and that's great. But what happens in the bloodstream when you have water and carbon dioxide is that it's going to make H2CO3 very quickly. This is carbonic acid. And so you'll make carbonic acid and you'll still have water in there, right? So then that carbonic acid is going to go in and make a conjugate base, right? So this is our same acid-base equations where we have carbonic acid and carbonic acid turning into the bicarbonate ion, HCO3 minus. This is our bicarbonate, B-A-I-B-I-N bicarbonate ion. This is the conjugate base, right? And so when we have that, we also have H3O plus. Because where did that other hydrogen go, right? We had 2 hydrogens here. We only have 1 hydrogen here. Where did the extra hydrogen go? It went to the water, right? So what do we say pH is dependent upon? pH is equal to negative log concentration H3O plus, right? So the more carbon dioxide you have in your lungs, the more what? The more carbon dioxide you have, not in your lungs, in your blood. The more carbon dioxide you have in the blood, what? The more H3O plus, so be careful, H3O plus the lower your pH is. So if you have a patient who comes in, and let's say this patient takes a whole lot of antacids. People take antacids to neutralize stomach acid, right? So antacids are like basically bases to neutralize stomach acid. That gives you indigestion, right? So if you take too much, it will go to your bloodstream and you will have problems. So what does blood pH change? How does it change when you take too many antacids? Antacids, we said, act as a base. So if I have a base and I add it over here to something that's very acidic, it's going to neutralize, right? But my blood was already neutral to start with. So what's going to happen? Blood becomes what? Basic. Blood becomes basic, right? Because you're going to neutralize it. This antacid is going to neutralize. It already neutralized all the stomach acid. It's just going to go to your blood and it's going to start neutralizing all the acidic ions inside of your blood. And so now your pH, your blood pH is going to become basic. This is not good. What do we call this condition? Metabolic alkalosis. Right? So which direction will the bicarbonate equilibrium shift when you take too much? It's going to shift what? It's going to shift to the left. That's exactly right. It's going to shift to the left. Why is it going to shift left? Because you're what? Yeah, you're depleting these hydrogen ions over here. You're completely depleting them. So you're going to shift left. Okay, now to treat this condition, patients are administered NH4Cl, which acts as a weak acid, right? If they overdose on base, you give them an acid. How does this restore our equilibrium? All it's going to do is increase, it's an acid. It's going to increase H3O plus. Right? You just give them the opposite and it has the opposite effect. So then in which direction do you shift as pH returns to normal? You shift to the right. That's it. That's all she wrote. That's the end of chapter 9. Okay, so next time I see you is exam. Don't forget to start studying for your final too, like over the weekend. After you finish the exam, start studying for that final. Let me know if you have any calculator issues. Come see me if you had calculator issues. I'm happy to help you. Let's see if I can read it. Okay, I should have put that down earlier.